we'll be back to our regular 6 o'clock schedule next week. Today, very pleased that we could have Professor Marina Di Giacinto. How do I do it? Good enough. Okay, so she received her PhD degree in applied math from Sapienza University of Rome. She's currently a tenured faculty member of the Department of Economics and Law at the University of Cassino. She holds a national qualification for associate professorship since 2018. She's been visiting the Laboratoire Ceramad at the Université Paris 9 Dauphine and the mathematics department at Root College of the City University of New York. Her research interests include the deterministic and stochastic optimal control theory applied to economics, finance, and insurance. Her papers are published in leading peer-reviewed journals like Finance and Stochastics, European Journal of Operational Research, Journal of the Operational Research Society, and Quantitative Finance. Marina, take it away.
Thank you for your invitation.
Sure.
And today I would like to talk about the category of optimal execution problems that can be stated as a linear quadratic optimal control stochastic problem. The result I will present comes from a project work with Shui Chang of Peking University and Tai Ho Wang of Baruch College. And we consider the point of view of an investor who aims to liquidate a large position of an asset by choosing a strategy. And a large investor often faces the problem of liquidate her position within a short period of time. But transactions in a large volume often induce an impact on price movement. To minimize the impact of her trade, the investor can split her position into small child orders and execute them in a longer period of time. However, a longer execution incurs an extra exposure to the risk of price movement. Therefore, the trade-off between the price impact and the price uncertainty is crucial. Moreover, an issue often overlooked in literature is that all the orders are fully executed. In reality, transactions may differ from the scheduled run, and we refer to such a risk, to such a deviation, as the uncertainty of order fields. And this risk is a different risk from the risk of price movement. Our optimal execution problem is stated as a stochastic optimal control problem, where the control variable, of course, is the investor's trading rate. The goal is to maximize the final profit and loss for risk-neutral or risk-averse investors, and since order fields are uncertain, we add a noise term to the evolution of the investor position. And since at the end of the execution period, there could be some orders that are not fully executed, there could be a final block trade to be set, the objective functional includes a penalty function for this final block trade. Therefore, our investor's position dynamics is driven by this stochastic differential equation. We have already have taken this, considered this kind of dynamics in a previous work published on quantitative finance in 2017. The dynamics here has V, that is the control variable, so the trading rate. M is the magnitude of the uncertainty of order fields. X0 is the initial position, so is the order to be liquidated. And capital T is the end of the execution period, namely the period at which the full position must be liquidated. We don't put any constraint on the trading rate. So the investor can liquidate actually more of the security than the shares initial held. To analyze the optimal execution problem, we need, of course, to specify a model for the evolution of the fair price and the traded price. We apply the dynamics of the seminal paper of Algren and Fries. So the fair price is described by this arithmetic Brownian motion, where gamma is the permanent impact, while the transact price is given simply by the fair price minus the parameter positive that represents the measure of the temporary impact multiplied by the trading strategy. The P&L, borrowed also from Algren and Fries model, is essentially composed by two terms. The first term is the fair value of the shares that the investor has to be yet liquidate. The second term is the transaction cost resulting from the shares that the investor has liquidated, has sold. Of course, if we don't have any trade during the time interval, the second term is 0, the X is 0, and so the profit and loss reflects simply the movement of the price of the stock. And in this framework, my target today is to show the results when we maximize a risk-neutral investor's profit and loss posterior to the final block trade, by taking into consideration the presence of inventory costs that are related to market makers operating over heterogeneous time scales. This is a first step to better approximate the traded price trajectory to the reality. Actually, it's a work in progress. Our aim is to approximate in the best way the traded price trajectory. And if time permits, a trade-off between the investor's profit and loss posterior to the final block trade and a dynamic risk measure. In this second,
I'm familiar with Algren and Fries, and I remember that they explicitly put variance in the objective function. Prices.
In the second part. Yeah.
Okay, in the second part. Okay, yes. And you're dealing with a risk-neutral investor, so obviously the risk-neutral investor does not care about variance.
Yes. Yes.
So I can see how a risk-neutral investor does not like price impact. But what is the offsetting? Since you're doing an optimization, you have to have two effects moving in opposite directions to get an interior sort of solution. So if you trade a lot right away, there'll be a big price impact, and that's bad. Mm-hmm. And if you don't trade a lot, what is going on? You're not getting not that you're suffering variance. So what are you suffering?
Actually, there is a problem that we solved with the variance and with the quadratic variation in the previous work in quantitative finance, the work published in quantitative finance. We consider we solved the problem with a utility function, and another problem with the quadratic variation. And in the same paper, we solved the problem for a risk-neutral investor when we have an uncertainty.
Yeah, I think I know the answer to my question. So
So
there's price impact.
the results in that case.
Or if you don't trade now, you're going to have the price impact with the block trade at the end. Is that those are the two things you're trading on? I think. Is that right?
Please?
Yeah. The two things you're trading off are the adverse price impact if you trade now versus the adverse price impact that you'll have at the end when you do the block trade. Right? So those are the two things you're trading off, I think.
Trading off?
Yeah.
No. No. In this second setting, we solve that problem. We introduce actually a dynamic risk measure that measure at any time the risk to not reach the full liquidation at capital T, at the completion time, at the end of the execution period.
Okay.
In this second setting, here we consider simply a risk-neutral investor's profit and loss because our target here is to better approximate the traded price to the reality, because empirical evidence show that the traded price decreases in this case because it is a sell program in a power law, more specifically in a square root law.
Okay.
And with the Algren increase setting, we have simply, I can show you, I have a picture.
Maybe you should set up the other use Acrobat for the other.
Okay. What happened? The price trajectory in a WeWeb execution, formulated as price execution, in a non-risk setting, the traded price simply decreases linearly, and then at the end of the execution time is constant. In our modified model with inventory cost, even if we maximize the profit and loss posterior to the final block trade, we have the traded price that decreases in exponential law. Then, at the end of the execution period, come back in a higher level in exponential law. This is still inconsistent with the reality because the empirical evidence show that actually this plot must decreases in a power law.
Okay.
But it is a first step to do that. This is the main target in this setting. This problem. Okay.
What is T equals 1? What's the significance of T equals 1 in this graph?
Pardon?
What's the significance of time 1 here? What is that point?
This is the completion time, the end of the execution period, when the full position must be liquidated. Okay? And here, reverse.
So there are other conditions like summation of B's is equal to x0 and eta is the transaction cost?
temporary impact. And gamma is the permanent impact. Okay? Actually, empirical evidence gives us this plot for the traded price. Decreases in power law and then reverts back to a higher level. This delta is the temporary impact, this quantity, the gap within these two lines.
How does it fight with the arbitrage arguments?
We didn't take care about the arbitrage argument.
Marina, question? So you're saying that, so you're not saying that you set a remaining amount to liquidate. You're saying that there's some strategy where you identify an optimal trading strategy,
yes,
and that leads to some remaining amount that has to be liquidated, right?
Yes, could be, because we have the uncertain of order fields. So what happens? That in an infinitesimal period of time, the investor's order can be overly or underly executed. This happens in an infinitesimal period of time. And at the end, what happens? That maybe some transactions are overly executed,
right,
underly executed. So we have a final block trade, and the investor has to take the final block trade at any price, and probably it will be a bad trade.
But like let's say over delta T, if a portion of how much should be traded, dx, doesn't happen, right? That means that that leftover amount, does it influence the amount that should be traded in the next interval? You know what I mean?
Yes,
okay,
yes, of course,
okay,
because it's a dynamic optimal execution. We solve the problem by applying the dynamic programming. So at any time, the strategy changes.
And includes the fact
yes,
of failure to trade in prior times.
Yes,
I understand.
which is the exact position today. The result is Markovian, the strategy. So we look at the state today, and then we decide how much to trade. Exactly to trade.
Thank you.
And in the second part, there is the answer to your question. Here, we want to better approximate this one. We can show that our model decreases exponentially, but we aim to reach a model that permits us to represent this plot as power law.
So, just to be clear, what you're actually graphing is the expected value of the price.
Yes,
right?
it's of course, it's the expected value, of course.
Yeah.
Otherwise, we should have like this, of course, make sure this is the expected
I was
value.
thinking the same thing.
So, this will consider actually that the spread between the reference price, the bid price, and the traded price consists in three components: the adverse selection, the inventory cost, and the processing cost. We don't take care about the processing cost because it is a fee, so it is a constant. And we consider the adverse selection and the inventory cost. The adverse selection comes from the linear and the temporary impact. And we model it, I showed you, like Algebraic model. And the inventory cost. To model the inventory cost, we borrow a result from Leal and Fernandez Tapia. Actually, they show that if the quotation of the bid spread and the ask spread is linearly respect to the inventory of the market makers, that strategy is suggestively optimal.
Okay. So now you've answered my question. So I was wondering what you're trading the adverse selection off against. And it's the inventory cost, right? So you have money tied up in the security that you have yet to sell. And there's an opportunity cost. If you had only sold that stuff, you could earn interest on it, let's say. So that's the inventory cost, for example. Okay. All right. Okay.
Well, wouldn't the other securities still earn that rate of return?
Depends on your model. Maybe. Okay. Like, I mean, it would if not for the selling that's causing the price to go down, right? So, yeah, let's say you had 2 shares to sell. Okay, and then you sell one, and that actually lowers the price that you're going to get for the other one. Yeah.
So we borrow the dynamic of the inventory cost from Quant and his co-authors. Actually, the diffusive limit of their strategy of the gives us a generator of an Ornstein-Uhlenbeck process. So we use as dynamic of the inventory an Ornstein-Uhlenbeck process. I will show you. Just to conclude.
May I ask you, why do you have on both stages on this process you have deceleration, not acceleration? I would say that if you sell one, if you sell, show on the first, this one. Why is first exponent is going with acceleration? Why isn't the first exponent is going with acceleration, not deceleration? It's like friction here, but on the first stage you should have not friction but acceleration in this process.
At the beginning, you mean?
In the beginning, yeah, because you sell one, after that you sell another one, and your price should be decreasing with acceleration. And at the end, you don't have counterparts who want to buy your security. So,
but this is a schematic block, of course.
Yeah, but it should be otherwise.
But it's
Yeah.
under the
He's
optimal
saying you're
strategy.
convex, and I think he's thinking it's concave.
Yes.
Right.
But it's under the optimal liquidation strategy.
But,
So
this
you
is a
don't
mark.
want to accelerate.
Well, you can't control your counterparts, and this trader has less and less counterparts.
There are some literature.
Counterparts. I mean, he or she has to sell securities to somebody. If there is no buyers, so price will be drastically decreased.
There is the buyer.
There is market makers. We have market makers.
Yeah.
Of course, has to buy if you want to sell.
Should be another
Their job, of course. And this is the empirical evidence. I mean,
Yeah. Think of it
there are
as
some literature
volume
about
discount.
this.
So the first
that
share
shows
has a big price impact. The second share, when you sell a total of 2 shares, total price impact per share is smaller. Right? That's what she's doing. And it's called it volume discount or something like that. As an intuition. So
it's not by our assumption.
But what I saw that was otherwise. If somebody tries to sell his big package of stock and there is no buyers, stock is falling drastically for some moment.
But,
and then it recovers like on the second stage. But on the first stage, if amount is large, it will be very fast and faster with every next package of.
yeah. But let's say, okay, so she's justifying this for two reasons. First, it's empirical. But second, I'm going to understand, there's an actual model that leads to this shape, right? So you're asking why is it like this?
But the permanent impact is
There are some literature that see as some papers say us that
In other words, you have your model, which is concave, but she has her model, which is natural Yeah.
The different ratios of the stock is going to be
permanent survives.
And so the spread between the traded price, between the reference price, the mid price, and the traded price has these components. In our increase model, we have only the adverse selection. In our model, we have adverse selection and inventory cost. And so we have this difference, okay? And of course, if we introduce n a finite number of market makers, we get an exponential law. But our aim is to address the Faber law case by introducing an infinite number of infinitesimal market makers with heterogeneous characteristic time scales. So, the evolution of the I market making inventory can be described by a non-stable event process, where theta, the mean reversion rate, can be interpreted as the trading speed of the I trader. Q bar, the long-term mean, can be interpreted as the proxy of the capacity, and Q0 is the inventory at 0. And it is reasonable to think that this quantity at 0 is 0, because the deviation should be 0 when the market makers just start to trade. By introducing these dynamics, the inventory cost for a finite number of market makers, we get this fair price. Without this part, the blue part, we have the usual arithmetic primary motion that has been introduced by Adrian and Chris. And we have this additional term. The transact price is the same, and so we obtain that the transact price is composed by 3 terms. This term is the reference price. The third term is the average selection, the part that comes from the impact, temporary and permanent impact, and the second term is the new one, is the term that comes from the inventory cost, as phi is the cost per unit of capacity.
So this new term, just trying to understand it. So the little q is some target for the quantity of shares held. Okay. Yeah. All right.
So Q is the long-term mean, and can be interpreted as a proxy of the capacity of a trader.
So Q, just capital Q, is it the quantity of shares traded, or what is it?
Capital Q
Yeah.
are the amount of inventory of each
the total
market maker.
inventory holding.
Yeah.
So positive or negative, it looks like?
Yes, it could
Yeah.
be positive, negative, of course.
Okay.
Of course.
And let's say on the next page, the cost is...
The cost is phi. Phi is the inventory cost per unit
Yeah.
of
So
capacity.
you're penalizing, deviating from either side.
Yes, of course,
Q-
because
Q0.
if this is negative, this is positive, and this
Yeah. Okay, that's fine. So let's say, let's keep it simple, little q is 0.
Yes.
And then if you have, then the absolute value of the inventory is the cost. Is that the gist of it?
No, it's not the absolute value.
Yeah, it's not the absolute value, I know.
It's not
So-
the absolute value, because
Right.
if you buy,
It
you
is, yes.
will penalize over
Yeah, that's
sold.
right.
If you
Okay.
sell, you penalize.
So I agree, there's no absolute value there. So that's what's bothering me, I guess. So, so there's a, like, if Q is very negative, then what sign is the inventory cost? Capital Q.
is negative, is positive.
Okay. And Q is instead very positive, I assume the inventory cost is the
Yes.
opposite sign.
Uh-huh.
So,
For example,
okay.
if a Q is positive,
Yeah.
means that the market maker has a certain amount of shirts. Okay, so if I want to sell other shirts, of course, for the market makers, it's not a good position because he has to buy additional shirts.
Okay.
And that's why the price goes down.
Okay.
And the opposite, this is the symmetric situation we
Oh, they
have
change-
in case of
Okay,
my
I see.
program, of
You're
course.
thinking like they're adjusting their bid offer spread to get the flow to drive the inventory to the desired little Q. Okay, that's fine.
Okay? Okay.
Yes.
Profit and loss, the definition is the usual, and after some computation you get this formula, just to show you. Okay? So, to formalize our stochastic control problem, we introduce the state equation. The state equation is written in a matrix form, and we make this simple change of variable of the inventory. This is a technical change because with this simple change we can represent our optimization problem as a linear quadratic optimization problem. Otherwise, we get an affine term in the objective function that cannot, don't allow us to represent as a linear quadratic and utilize some even result in literature. So we make this simple change of variable and we represent the state equation in a matrix form. X is the vector that contains all the state variables.
How many shares?
The state
The
vector.
person trying to sell.
The trader.
So, we solve the problem by applying the dynamic programming method. The objective functional is the expectation of the profit and loss earned over the time interval small t up to the completion time, up to the end of the execution period. Adjusted by the penalty function for the final block trade. I skipped because okay. We talked about the penalty function. We assume that as this shape is a quadratic function, beta x squared. Beta, of course, is a positive parameter, and this penalty is 0 if and only if there is no
trade.
No trades at the end. The position is completely liquidated, and it it is positive either if we are a negative position, even if we are in positive position, because I recall that we don't put any constraint on our strategy. So this is our objective. The set of admissible strategies is simple, since we don't have a constraint. The set of progressively measurable real-valued processes. The final objective functional is this, and it is quadratic with respect to the state variable, and quadratic also respect to the optimal, respect to the control, because x includes the position, and in the dynamics of the position we have the control strategy.
Yeah.
Okay? So we have to maximize the functional, and the optimum function of this class of problems is the value function. The value function that by standard argument solve a given Hamilton-Jacobi-Bellman equation. In our case, the Hamilton-Jacobi-Bellman is a second-order partial differential equation. One of the solutions of our AJB equation is given by this quadratic function, this concave function, under the condition that beta is the parameter of the penalty function, and gamma is the permanent impact. Under this condition, this quadratic function, this concave function, solve our AJB equation. Capital R is a symmetric matrix, and R is a vector. Then R unique solution, we show that R unique solution to a given system of Riccati ordinary differential equation. And we can compute explicitly both of them. With that value, with that function solving the AJB, the corresponding Friedman map reads as this one. The
What's
Friedman map.
N here? N. N. What is N?
What's
N.
N? N? This N?
Yeah, what is it? Number of what?
Is the number of the market makers.
You have a few market makers
We have N market makers.
who wants to sell this stuff?
No, market makers.
All in the market.
In the
All
market,
in the
we
market.
have N market makers. So this is the state variable x, and we have N market makers plus the position.
But how do you know what every one of them want to do? Maybe somebody buys, somebody sells, what? Somebody
No,
look
we have
at.
an investor. We have simply an investor.
You have only one investor
We have an
with
investor,
selling.
and she wants to liquidate her large
So
position.
this is one.
In a market where we have a multiple number of market makers. We have multiple market makers and market makers, a finite number. Okay?
Yeah, so let's say, her state variables are not just the number of shares in your inventory now, but moreover, what all of the end market makers are each holding, right? The Qs for each market maker. That's your, that's a complete description of your state variable. So you would, let's say, freeze your inventory and you change what some market maker quantity L is. That changes what you do. Okay, because it affects the price you're going to get when on your trading.
But they're dependent on nothing. They
Yeah.
want, they are all waiting. Somebody is selling stock, so they are looking at him, and now and here they are independent. So it's very strange.
Like, she's trying to capture, let's say, two extremes. Like, first, let's say every market maker is right where they want to be. Okay, so then, let's say you get one set of prices when you do a trade, versus every market maker is very far from where they want to be. Okay, then you see very different prices. Okay.
So with this map, the corresponding closed loop equation read like this. And this closed loop equation has a desirable feature. It has a unique solution. Thanks to the uniqueness of the solution of this closed loop equation and of the linearity of the feedback map, the feedback map computed evaluated in the unique solution of the corresponding closed loop equation is an admissible strategy. Okay, is there? I don't know if I can. Okay. So since it has a unique solution, the fitment map evaluated in the unique solution is an admissible strategy. But we can show more. We can show that actually the fitment map computed evaluated in the unique solution of the closed loop equation is the unique optimal strategy. This comes from thanks to the fact that we show that the previous function, quadratic function, concave function that solves the algebraic equation is actually the value function.
And do all the market makers have different target prices in a sense? Do all the market makers, you have put one parameter associated with every market maker?
Yes, I have theta. Theta represents the characteristic of any market maker. Theta I.
So they all have some targets.
The version rate. So it's different. They are heterogeneous. So they are representing each market maker is represented by theta.
That might give rise to that change.
This is the optimal strategy in feeder form. Some consideration, it doesn't depend on the volatility of the inventory. Is actually an adaptive VWAP, volume weighted average price, scaled by a function of time. And when phi is equal to 0, not inventory cost, we have this strategy that is exactly the strategy we found in our previous paper, in quantitative finance, where there is no inventory cost. But what is here the most important is this one, this term. The sum of exponentials respect to theta gives us a traded price that decreases in exponential law. Is exactly this term. However, our aim is to get a power law. And it is possible to have it considering the limiting case. when we have an infinite number of infinitesimal market makers with heterogeneous characteristic time scales. We can show this fact here. Actually, is a guess, because this is a work in progress. Because to show in rigorous way, we should solve a stochastic control problem in infinite dimension. However, if we consider
is an intuition that
yes,
say,
it's,
well,
yes, it's a guess.
Like,
it's a guess.
No,
it's a guess.
Okay, let me just say
because it is a work in progress. Up to now, we can see that the traded price decreases in exponential law.
Yeah, let me just say something.
Okay.
So you've got these exponential laws for each market maker. So let's say, as you wrote, you have a superposition of exponentials. So there's something called like real Laplace transform. It says you want to represent a function, you can represent a big class of functions by weighting using real weights, exponential functions. Okay, so like I'm thinking if you just maybe if you're looking for how to do it, you look into the literature on representing a given function using superposition of exponential functions, which is basically a real value of Laplace transform.
Yes.
Okay. Okay.
Okay. And if we assume that the characteristic time scale of any market maker theta I are a sample of independent realization of random variable distributed as gamma distributed with parameter mu, and the procedure is not new, is borrowed from Anderson and Robertson. They applied this procedure in financial markets volatility. And we compute the limit as n goes to infinity of the sum of the inventory. This limit, by the law of large numbers, converges to the cross-sectional mean across market makers, defined by this integral, where here there is the density of a gamma function. And similarly, we can compute the limit of, as n goes to infinity, of the optimal strategy and we have at the end an expected value actually of the traded price like this. This term plus a custom plus a lower order term. I didn't write them because are too much and we don't care about that. And this give rise to a square root law. I simply plot by setting u equal to 1/2 and capital T equal to 10.
Okay.
And actually we have a square root law.
Okay.
Just a quick consideration about the second problem. We introduce the most important feature of this result is the solution of a non-standard stochastic optimal control problem. Because by adding this dynamic risk measure that measure at any time the risk to have at the end of the execution period a final block trade, you don't have to the full liquidation of the position. And the standard, the backward part, comes from the fact that a risk measure, we apply an entropic risk measure, is a unique solution to a one-dimensional backward stochastic differential equation with quadratic growth. And what we have, we solve the problem. And in our problem, we have a state equation that has a forward part and a backward part. The solution, we get the solution of the optimal strategies. And we have also some picture and some consideration, some plots of this strategy, but people who is interested in this argument can give a look to the paper. It has just been published last October on Quant. If somebody is interested, I can send the paper. So, I think the time is over. Just the last one sentence. The last but not the least. Thank you for your attention.
Oh, right on time. No, are there any further questions? All right. Well, thanks again.